Hey everyone, it's Colt. I'm back from my not so short break. It was supposed to be like a week. It turned into 2 weeks. Life got in the way. I moved. My studio is sort of set up. It's like the only thing currently unpacked, but it's good enough. So I have a video here on big O notation. This is a very important topic. I get asked about it a lot. I use JavaScript as the language for some of the code snippets in this video, but there's nothing really JavaScript specific about this topic. In other news, I have a new video coming out most likely next week on Webpack. Something I get asked about a lot, something I see in the comments and the polls. Oh, and I'm very excited to say that I'm almost done with my React course, a very big React course. It won't be on YouTube, but there will be lots of React content on my YouTube channel in the next few weeks and months. I'll have more information about the course as I finish editing and launch it, so you'll know. And while I have you here, please subscribe to the channel, turn on notifications, comment, share with everyone in your family, your friends, your school, your church, your job, your world. I do spend most nights just compulsively refreshing my YouTube channel, seeing if my subscribers go up or down, if my likes go up and down. It's the only way I derive my self-worth. So please like and subscribe. All right, I'm just kidding, but it does make a big difference. Enough of the chit chat. Let's get on to the notorious BIGO notation, big O notation. So where's a good place to start? Well, imagine that we have multiple implementations of the same function, 10 different variations. They all work and they're all different. How do we know which one is best? Here's a more concrete example. Write a function that accepts a string and returns a reversed copy of that string. There are many approaches to doing this. In doing some Googling, here's a Stack Overflow post I found with 10 unique implementations, all different. So I'm not talking about, switching out a for loop for a while loop, changing variable names. These are completely different approaches. How do we compare these? How do we know which one is best? What does best even mean? It would be nice if we had a little scale, a chart on the wall when I'm teaching that I could point to and say, you scored green for great, you scored orange for that sort of thing. But we don't quite have that. But it's kind of what big O notation is going to help us do. It's going to help us talk about our code and compare our code. So why should you care? Well, it's important to have a good vocabulary to talk about how your code performs, especially when you're talking about trade-offs between different approaches and you're trying to make decisions about which road to go down. Also, if you have an understanding of what makes your code perform well, what speeds things up, what makes it slow, it will also help you a lot when you're trying to debug things. You'll be able to find bottlenecks and pain points. Finally, and this is probably one a lot of you who are watching this care about, big O notation comes up a lot in interviews. It's not my favorite topic personally, but that doesn't stop a million people from asking it all the time. All right, let's look at some simple code. 2 functions that calculate the sum of all numbers from 1 up to and including some number n. So here's our first one. It uses a loop. We loop n times, and we have a total variable, starts at 0. Each time through, we add whatever our loop number is to that total. So it starts at 0, then we add 1, 2, 3, 4, all the way up until we hit n, and we return total. The second version is shorter, a lot shorter, and it uses some magic mathematical formula. I had a slide on how you derive this, and I ended up removing it just to keep this video nice and brief. But trust me, this works. We take n, whatever it is. Let's say it's 3. We're going to multiply 3 times 4, which is 12, divide by 2. That gives us 6. The same answer we get over here. 3 plus 2 plus 1 is 6. Okay, so they both work. You can trust me. How do we know which one is better? Well, it's sort of complicated, because what does better mean? Is it the faster algorithm, whichever one finishes first? Is it the one that takes up less space, less memory on our machine? Is it one that's more readable? Is it one that is shorter? The number of lines, does that matter? For this video, we're going to be focusing on speed, what we'll call time complexity. I'll touch a little bit on space complexity at the end, but we're really focusing on speed. So it seems like a good place to start would be using timers. We could simply grab the current time, performance.now, and then call add up to, and then grab the current time after it finishes, immediately after, and then subtract the 2, and we should be able to tell how long it took, and then we could try that on the other version and compare them. However, it doesn't really work that well. The problem with time sounds like a title of an album an aging rocker would come out with at the end of their career, but really, there are some problems with timing our code. First is that different machines will record different times. Second, the same machine will sometimes record different times. I'm going to show you this in just a moment. Also, sometimes our algorithms are so fast that testing them with a timer is not going to be precise enough. So here's a nice little tool some of my friends at a boot camp called Rhythm School made. That's not an ad, I promise. So this tool allows you to select one of those methods. So here's our first add up to that uses the loop. And here's the second one we're talking about with the magical mathematical formula. And what we can do is pass in a number n, and it will time it and plot how much time it takes on a chart. So let's start simple. Let's plot 1. And then what about when we pass 2, 3, 4, 5. Whoa, what happened to 5? Why'd it go down? 6. Why is this getting slower as we go? And then coming back up, it just doesn't make a lot of sense. It seems highly unpredictable. And that's mainly because this is happening so quickly, our JavaScript timer is just not precise enough. In addition, if I try 10 again, so 10 was apparently very quick the first time. If I try it again, this time it was like a lot faster. One more time, it keeps moving up. Wow, that was way faster. So my point here is that it's highly unpredictable. And now if we add in our second version, let's see if it's any better. So I'm going to speed through this. Plot 2 and 3. Okay, so I fast forwarded just a bit. I plotted all the first 10 numbers on this other one, add up to second. You can see it's just as unpredictable. It's up and down, it's hot and cold, it's yes and no, it's changing all the time, and it doesn't really give us a good idea of which one is better. However, we can get a much better idea if we zoom way out and we make our numbers way, way larger. So let's go back to the first one and test 100. And then 1,000, and then 10,000. And let's just keep adding zeros. I will warn you, if you play with this tool and you start using really large numbers on some of these other examples, your browser's not going to have a good time. So just be careful. You can see it's starting to take a lot longer. And I'm going to stop here because the next one will take a couple of seconds at least. Now let's go to our second version with the fancy math and do the same thing. So we're really just looking at a much further zoomed out, much bigger picture view to try and get an idea of how they perform. And this is not at all practical to actually test your code this way, but I don't know if you can see the gray down at the bottom. It's way, way, way down there. And at this point, we can see there's a clear trend. This gray one is way faster overall. When we zoomed in to the first couple digits, it was really unpredictable, up and down. It didn't make a lot of sense. We couldn't really decide which was better. But now that we're way zoomed out, we can tell definitively this one is much faster overall as we make n way bigger, as we approach infinity. And that's the approach we're going to take in evaluating our code. We're going to think about how it performs as it gets towards infinity, as the input n grows to an insane level. But of course, we're not going to make a graph and chart our code every single time we want to understand how it performs relative to other code. So instead of working with time, what we're going to do is work with the number of operations. We'll be able to determine how something performs just by looking at it, without actually having to run the code, without having to print a graph or a chart. We'll be able to look at it and roughly approximate what that chart will look like if we were to plot it. So we count the number of operations with a very simplified way of counting, as you'll see in a moment. So this second example, the simpler one that was much better on the chart, only has a couple of operations, one multiplication, one addition, one division. And it doesn't matter how large n is. If n is 1,000,000 or if n is 5, we have the same number of additions, multiplications, and divisions. It doesn't change. So we would say 3 simple operations regardless of the size of n. If we compare that to this example, as n grows, we have a loop. And this loop is dependent on the value of n. So we have n additions inside of that loop. If n is 1,000,000, we're adding 1,000,000 times. We have n assignments, we have n additions and assignments up here in the loop, we have 1 assignment at the beginning. It doesn't really matter what the exact number is. We're looking at big picture trends. But you can see that as n grows towards some large number approaching infinity, this number of operations we're going to have to do is going to grow at least in proportion with n. So on the last slide, the number of operations was somewhere between 2n and 5n plus 2 if you were trying to be exact. But it doesn't matter because as we've already discussed, it's just about what that big picture graph looks like. And as n increases, the number of operations we have to do is going to increase roughly in proportion with n. So now it's time to officially introduce the definition of big O. Big O notation is a fuzzy way of formalized counting. So we say fuzzy because we're not being very specific. We're just zooming way out and we're imagining what the number of operations looks like, what that chart looks like as n gets way larger. And it's just a nice way of describing, sort of pointing to that chart that I showed you at the beginning, saying this is good, this is mediocre, this is this is terrible. Except instead of saying, green for good and orange for meh, instead we actually describe it with a mathematical function. So here's the actual definition. We say that an algorithm is O of a function, f of n, if the number of simple operations the computer has to do is eventually less than a constant times f of n, the function, as n increases. What this is really saying is that there's some function. It could be a linear function of n, it could be a quadratic function n squared, it could be a constant function of just 1. Whatever this function is, when we say something, an algorithm has O of n or O of n squared, O of that function, we mean that as n grows, the amount of operations, the time it takes, is going to grow roughly in proportion with this function. And I should mention there are many other options. This can be pretty much anything, but there are some common things you'll see, like the ones I've listed, and I'll run over them at the end. Okay, so let's talk about this example, the add up to n. We saw that there was 3 operations no matter what the size of n is. But remember, we want fuzzy counting. We just want the big picture. So we would call this O of 1. What this means is that as n grows, if n is 10, if n is a million, if n is a trillion, whatever comes after a trillion, it doesn't matter. The number of operations we have to do stays the same. And if we were to plot that on a chart, it would look like a completely flat line. There is no increase in the amount of time it takes, the number of operations, as we move towards a larger n. Now, if we compare that with this one, add up to n, where we have a loop based off of n, we know that the number of operations is going to grow in proportion with n, some multiple of n. It doesn't matter if it's 10n, 1n, or 50,000 n. It doesn't matter, we just want the general trend. So as n grows larger, so does the number of operations. So this is called linear time, where the line looks something like this. A sort of diagonal line, or not sort of, a diagonal line, where as n grows over here, the number of operations it takes to calculate the result is also going to grow in proportion, versus our first one we saw, which is constant time, is always the same, roughly. We saw the reality of it. It was not exactly the same. It was different every time. But when we look at the trend, the function we would use to describe this chart, this line, is f of n. So here's another example. Count up and down. It takes a number n, and it prints all of the numbers from 0 until n, and then it does the opposite going down. So it goes from n down to 0, and it prints all the numbers. In this case, we have 2 loops. The first one is going to be O of n. The second one is O of n. So you might think we would say this has a time complexity of O of 2n, but we only care about the big picture, and we simplify it down to O of n. It doesn't matter. Once again, if it's 2n or 1000n, it doesn't matter in the grand scheme of things, because as n grows towards infinity, this coefficient in front, whether it's 10 or a million, is so small and insignificant, we just describe it as O of n. Finally, another example, a little bit different, we have a nested loop. Never a good thing to see if you're trying to write fast code. So we have print all pairs, which is just going to print all the pairs of numbers between 0 and n, like 0, 1. 0, 2, 0, 3, and then 1, 2, 1. Anyway, we have our first loop that runs n times, and each time through that loop, we have another loop that runs n times. So this means for every n that we put in, we're going to have to run n squared operations, roughly. So when you have an O of n instead of an O of n, when you have a nested loop, we're talking about O of n squared, which is called quadratic time. And if you can think back to, algebra is when we learned that, trigonometry or something, very, very steep line is what O of n squared looks like. So I'm going to refresh the page here, and I'm going to start by printing all pairs. This is the one I just showed you that had O of n squared. And let's try doing 10 and then 50. You got to be very careful with this one because n squared grows very, very quickly. So far it looks like it's linear. But as I start adding larger n's, you can see what's happening. Let's go up to maybe 250. See how much time it's taking already? 280. I don't even want to go to 300. My computer is not going to be happy. Okay, so if we look at this chart, it doesn't look that steep. But now Let's also add in our first example, add up to first, which was O of n. This is linear time, so as n grows, the number of operation grows roughly in proportion with n. So let's try 10, and then we'll try 20. And now let's try 50. Okay, how about 100? 1,000. 10,000. Take a look at how much faster this is compared to n squared. N squared is this one up here that looks almost like a straight line at this point. N squared is going to grow extremely fast. So here's a chart that shows some of the most common big O functions, some of the most common time complexities. So this first one down here is constant time, O of 1. That's great. If you can write a function that takes the same number of operations no matter what n is, and it works, then you should absolutely use it. But most of the time, we can't. Sometimes we can, but it's often very difficult. So this one here, O of log n, we haven't talked about logs in this video, but log n and another one called n log n come up often when we're dealing with more advanced data structures like trees and sorting algorithms. So I'm not going to go into it here, but I just wanted to show you what it looks like. It's good as well. If you can have a time complexity of log n, it's almost ideal. Here is linear time, O of n. So as n grows to 50, the number of operations roughly grows to 50 as well. We get that nice 45-degree angle line. Then we have n log n. Again, this comes up in more advanced data structures and sorting algorithms. And then our worst nightmare, quadratic time, n squared. This is going to grow extremely quickly, and you want to avoid writing algorithms as much as you can that have a time complexity of n squared. It's not good. There are some helpful rules that you can keep in mind when you're trying to determine the time complexity of an algorithm. So, first one is that constants don't matter. O of 2n, it's just O of n. O of 500, that's just O of 1. O of 13n squared, it's just O of n squared. Remember that these numbers are inconsequential when n is getting massively huge, N is skyrocketing. 500 doesn't mean much compared to 1, especially if n is a million or a trillion, even though that's not a real number. Similarly, smaller terms don't matter. O of n plus 10, that's just O of n. O of 1000n plus 50, just O of n. O of n squared plus 5n plus 8, getting tricky here. It's only O of n squared. Smaller terms don't matter, and 5n is way smaller than n squared. If you ever have any doubt in your mind, try plugging in a very large number for n, and just compare the difference between n squared and then 5 times n. The general trend is just O of n squared. There are a few more rules or shorthands you can keep in mind when you're trying to determine time complexity. I am going to breeze through them pretty quickly. It is just a short YouTube video. The first is that arithmetic operations are constant time. So if you're adding something or subtracting something, you can assume, or multiplying or dividing, it doesn't matter what n is. If n is 1,000, if n is 1,000,000, or if n is 5, just assume it takes the same amount of time. Same thing with variable assignment. Also the same thing with accessing elements in an array or in an object. It's constant time. That's the way those objects work. They give you very quick lookup. Same thing with arrays. Now in a loop, the complexity is the length of the loop times the complexity of whatever happens inside of that loop. So if a loop happens n times, we're going to call it O of n. But if there's something nested inside of it that happens n times, then all of a sudden we're talking about n squared, as we've seen. All right, pop quiz here. Couple examples I'd like for you to try and think about how this function works as n grows. What's that line going to look like on a chart? What are we talking about here? Remember, fuzzy, big picture counting, zoom way out. This one is called log at least 5. So you pass a number in, n, and all that it does is it loops at least 5 times and more if n is larger than 5. So we take the max of 5 and n. So if n is 10, we'll be looping 10 times. If n is 1,000, we loop 1,000 times. But if n is 2, we're going to loop 5 times. So how would we simplify the big O? What is the answer? It's just O of n. It doesn't matter that we are looping 5 times when n is 1, when n is 2, when n is 3, because that's so inconsequential compared to the grand giant scheme of things. All right, pop quiz part 2. Log at most 5. How does this one work? It's going to take the minimum of 5 and n. So if n is 10, we're going to loop 5 times. If n is 1,000, we loop 5 times. If n is 2, then we're going to loop 2 times. So how would we describe the big O of this function? O of 1, it's constant time. So we loop n times if n is less than 5. But after we hit 5, if n is 6, 7, 8, all the way up to 1,000,000 or anything higher than that, we're going to be looping 5 times every time. But we don't say O of 5. Remember, we just simplify down. O of 1, constant time. This will generally take this exact same number of operations no matter how large n is. So this has been a very quick introduction. I have a whole course on algorithms, and I spend probably 10 videos just talking about big O notation, time complexity, something called space complexity, which I'll touch on in a moment. But I just want to recap what this shows us here. These are some of the most common functions in big O notation, but it's not limited to these here. But as we write code and we think about how it performs as n grows to some insanely huge number, if we can extract that and assign it a general fuzzy value, like, okay, this one is going to be O of 1, and this other solution we have is O of n, we can tell that this one is always going to be, or almost always going to be, faster. This is the better algorithm if we're talking about time complexity, compared to an algorithm that has linear time, for example, and especially quadratic time. So I'll touch on space complexity briefly. It's the same idea, except we're focusing rather than on the runtime, rather than the number of operations, we're talking about the size, the amount of memory we have to allocate as n grows. And that's all I'm going to do here on space complexity. It's the same idea. We think about n growing to a massive number towards infinity, and we try to assign it a function that describes how the amount of space, the amount of memory that it uses is going to grow. Alrighty, thanks for watching, everyone. I hope that made some sense. I know it was a lot to cram into a single video. If you enjoyed it, please like the video, subscribe, do all of that. I really appreciate it. And next week, I should have a video out on Webpack, so you can look forward to that if you care about it. And that's it for me.